Hello, I'm John Hickey.
I'm Ryan Edwards.
I'm Caitlin D. Herrera.
And I'm Jared Christner.
For our senior project, we designed and built a spring-loaded camming device. The purpose of this video is to go in-depth about our design process and how we tested our final design.
Cams are used by rock climbers to catch themselves during a fall. A climber will place a cam in a crack in a rock face where it can wedge itself between the walls of the crack when the triggers are released. This provides the climber with several anchor points. The market lacks camming devices that can be placed in cracks greater than 6 inches. Of those that are available, many are too heavy, low quality, or uncomfortable for regular use. Thus, our goal is to improve on former designs and produce a camming device that is strong while being as lightweight as possible and has a flexible stem which makes it easier to place the cam in a safe spot. We are excited to present our camming device that we call the ThickCam No. 9. It's a double axle, 4-lobe cam with a flexible steel cable stem. The cam is designed for 14 kilonewton load, weighs 2 pounds, and is usable within cracks between 6 and 9 inches wide. In addition, we also designed the cam to be able to be assembled without power tools, which makes maintenance and iteration easier as we can simply swap the parts between the cams.
The key component that separates our cam from others is the dual rotating trigger mechanism. With conventional triggers, a large cam requires the triggers to be pulled a long distance before the lobes are fully contracted, making it hard to use especially for those with smaller hands. With the rotating triggers, they can be located closer to the thumb loop, making it easier for smaller hands. After our second prototype, we saw that the triggers were unable to fully actuate the lobes, so our next iteration we implemented a double hinge system, which increased the pull range of the triggers without significantly increasing their size. When designing the carriage, we started with the basic double axle design. For the same lobe sizes, double axle cams have a larger usable range than those with a single axle. To optimize the carriage, we used Abacus to run FEA analysis to determine where the stresses were concentrating. We found that the region between the axles saw very little stress, so on our next iteration, we made the carriage more of an I shape to reduce weight.
We performed a similar process to determine the thickness of the cam's lobes. Since the cam's lobes are under compression when the climber takes a fall, we were concerned about the lobes buckling. To determine the proper thickness to avoid buckling, we modeled a lobe in Abacus and performed both stress and a linear buckling analysis at multiple lobe thicknesses. We found that the lobe reaches its yield strength before it buckles, and the minimum lobe thickness is about 0.4 inches. We used a variety of manufacturing techniques to construct our final prototype. On campus, we CNC'd the cam's lobes and using a manual lathe, turned down the axles. The triggers were 3D printed by Cal Poly's Innovation Sandbox and Joe Blakewell. The other components were either purchased or modified by hand. At the end of the winter quarter, the only components left to manufacture were the carriage and the axle links. Since we did not have access to campus facilities due to COVID-19, we outsourced the last of our machining to Rogue Engineering. Now Jared will summarize how our final prototype held up against our design specifications.
Early in our design process, we established the following 6 specifications that we wanted our design to incorporate. The 2 specifications our cam did not meet were the tensile strength and weight requirements. Unfortunately, due to COVID-19, we were unable to complete the cam's tensile test as we did not have access to campus facilities. The tensile test provides a ton of valuable information about how to improve the cam's design. Thus, we are looking into sending our prototype to another cam manufacturer over summer in order to tensile test it. Our cam weighs in at 1,134 grams, or about 2.5 pounds, a bit over our 900 gram specification. However, if we were able to further iterate and optimize the design, we are sure we'd be able to meet our goal. Ultimately, during this project, we learned how invaluable it is to build early prototypes, as having a physical object to manipulate and test significantly cuts the amount of time speculating an idea's feasibility. Prototypes also provide the team confidence in the design direction and their analysis. We also learned not to be afraid of reaching out to others in industry for advice and assistance. On multiple occasions, we were astounded by how willing others were to help us achieve our goal of building our camming device. Another factor that really helped us as a team is that we strived for open feedback and respectful criticism. We wanted to make the best camming device possible, so we were willing to change our behavior to make sure the team was working cohesively.
Thank you to everyone who helped us complete this project. Special shoutouts to Miles Whitman,
Our faculty advisor, Sarah Harding,
Noel Rhodes,
MESVAC,
Cal Poly's Mechanical Engineering Department,
Professor Treon Georgiow,
Eric Davidson,
Professor Kevin Williams, Tom Barsh,
Dr. Andrew Duvall.
Cal Poly Innovation Sandbox,
and Joe Blakewell. Again, thank you for all your help.